Video is on example 5 from section 4.5. In a swim and run biathlon, Jill must get to a point on the other side of a 50-meter wide river, 100 meters downstream from her starting point. So I drew the 50-meter wide river. Okay, in a swim run biathlon, that means she's going to have to swim across the river and then she's going to run the rest of the way to the finish line. So she has a starting point. I'm going to say that this is the start of the race. Okay. And the finish is 100 meters downstream from her starting point, but on the opposite side. So 100 meters downstream, let's say that that's 100 meters from the start, but on the other side. So this point on the opposite side of the river will be the finish. Okay, so Jill can swim at a rate of 2 meters per second and run at a rate of 5 meters per second. Pretty fast. Toward what point on the opposite side of the river should Jill swim in order to minimize her total time? Okay, so there's a lot of information in that last sentence, actually in the last two sentences. So we're given information about the rate at which she can swim and the rate at which she can run. We want to determine where she is going to swim to on the opposite side of the river in order to minimize her total time, right? So we are trying to optimize her time, and specifically we are trying to minimize it. So figure out how she can take the least amount of time. So I'm going to write that down. We want to minimize her total time, which means that we're going to need to come up with an equation for time, for her, the total time it takes for her to complete this biathlon. Now, we're also being asked toward what point on the opposite side of the river. So she's going to swim across the river. She might swim directly across. She might swim at an angle. It might be the most efficient for her to just swim the entire thing and not run at all, though that's probably not going to be the case. Especially the fact she can run faster than she can swim. So we're trying to figure out what point she's going to swim to. So I'm just going to pick a point on the opposite side of the river. And this green point here, I'm going to say is the point that she's going to swim to. Okay, so from the starting point to that point on the other side of the river. I'm going to call the distance from the starting point to the point that she swims to, I'm going to call that distance y. And now we know that from the starting point to the finishing point is 100 meters. So I can label the opposite side of the river, like I can label the distance from the starting point to where she swims to. I can call that distance x, or you could choose another variable, it's up to you, which would then make the distance from the point that she swims to the finishing line 100 minus x. Okay. So now going back to the quantity that we're trying to optimize, right? We're trying to minimize her total time for completing the race. So let's think about how we could come up with that equation. So the total time I'm going to call capital T. That's going to be equal to the time it takes her to swim across the river plus the time it takes her to run. Okay. We're given information about the rates at which she swims and runs. Okay, so we also have our handy dandy equation for distance equals rate times time. We're going to use that to help us here. Right, so distance equals to rate times time, right, or D equals to R times T. Well, we want the time to swim across the river and the time to run, and we're given information about both of those rates and about their distances. Well, sort of, we have ways to represent their distances. So if we were to solve for T in that equation, right, T ends up being equal to distance divided by rate. So to rewrite our optimization equation, the distance that Jill would swim would be Y, and then she swims at a rate of 2 meters. So Y divided by 2 would represent the time it takes for her to swim across the river. The distance that she's going to run is going to be this stretch here. So we've represented that as 100 minus x. And the rate at which she runs is 5 meters per second. So 100 minus x over 5. Now, our optimization equation has two different variables in it, right? Total time is in terms of x and y. So we are going to need to use a secondary equation. So we need another equation that relates x and y so that we can solve for x or y to replace one or the other. Looking at our picture, you might have noticed that we have a right triangle created here. Okay, where the distance, that 50 meters from one side of the river to the other, is one leg of the right triangle. Oops, didn't mean to move that. How do I make it? There we go. And then x would be the other leg of the triangle, and y would be the hypotenuse. So using Pythagorean theorem, we can come up with our secondary equation, right? That x squared plus y squared, x squared plus 50 squared would be equal to y squared. And it's probably going to be easiest for us to solve for y, especially since in our time equation, we could just replace that y. So since y represents a distance, y is going to be positive. So y would be equal to the square root, the positive square root of x squared plus 50 squared, which would be 2,500. So this is my secondary equation. We have solved for y so that in our optimization equation, we can replace the y. Okay, so we would have t equals to the square root of x squared plus 2500 divided by 2 plus 100 minus x over 5. And I want to rewrite that just to make it easier for me to think about taking the derivative. So I'm going to pull the 1/2 out front and change the square root to be the 1/2 power. And then I'm going to split up that fraction. So 100 divided by 5 is 20. And then we would have minus 1/5 x. Okay, so we're ready to take the derivative. T prime. Okay. Thinking chain rule for differentiating the 1/2 times the quantity x squared plus 2500 to the 1/2 power. That would be derivative of the outside. Leave the inside alone. Times the derivative of the inside. And then derivative of the constant 20 is 0. And then derivative of minus 1/5 x would just be minus 1/5. And we, of course, need to use our algebra skills to simplify. So I'm going to first rewrite that product without the negative exponent. So 2x would be left in the numerator, 4 is in the denominator, and then the x squared plus 2500 to the 1/2. And to simplify, 2 goes into 2 once, 2 goes into 4 twice. So we would have x over 2 times x squared plus 2500 to the 1/2 power. Or you can rewrite that as the square root if you prefer. I'm going to leave a little bit of space because we're going to be trying to get a common denominator. Because right now we have a difference of two fractions and we want to write, in order to find our critical values, we want to rewrite this as a single fraction. So I'm thinking about how I can get a common denominator. Well, for the first fraction, I could think about multiplying by 5 over 5, right, to get the factor of 5 in the denominator. And then I can multiply the 1/5 by 2 root, not root, I'm using 1/2. 2 times x squared plus 2500 to the 1/2 power over itself. So I end up just multiplying by the opposite denominator, that version of 1. So our numerator will become 5x minus 2 times x squared plus 2500 to the 1/2 power over 10 times x squared plus 2500 to the 1/2 power. And again, if you want to change that to be square roots instead of 1/2 power, that's totally fine. Okay, so that's t prime. And to find our possible critical values, we're going to figure out where t prime is undefined by setting our denominator equal to 0. So that would be 0 equals the denominator. And we're also going to find out where t prime is equal to 0 by setting the numerator equal to 0. Okay, so there's actually no real solution. There's no value for x. That can kind of, just looking at that equation, we could determine that there's no real solution. To 0 equal to the denominator, right? There's no real number that you could plug in for x that would make the right-hand side equal to 0. Now you could divide by 10, you could square both sides, and then you get x squared equals to negative 2,500, which means there's no real solution. You can't have x squared equal to a negative number within the real numbers. There's no real number that would make that a true statement. And then over here, where we have the numerator set equal to 0, we can subtract 5x from both sides. Okay, and then if we divide by negative 2, that will give us 5/2 x equals to the quantity x squared plus 2,500 to the 1/2 power. And here we can think about squaring both sides of the equation, and we would get 25/4 times x squared equals to x squared plus 2,500. And now this is turned into a quadratic equation. So let's get the x squared terms on the same side and think about subtracting x squared from both sides of the equation. So 25/4 minus 1 is the same as 25/4 minus 4/4. So that would give me 21/4 times x squared equals to 2,500. And then if I multiply by 4 over 21 on both sides of the equation, I would get x squared equals to 10,000 over 21. Almost there. And then remember, x represents a distance. So x is going to be positive, so x will only be the positive square root of 10,000 over 21, which is approximately, here I just want to make sure all my calculations are correct. Yeah, is approximately 21.822. So we have one well, actually, it would be plus or minus, but the thing is, we know that x represents a distance, so x can't be negative. So that reminds me, I need to make sure I'm stating my constraints on our optimization equation. So let's think about what the domain would be. Like, what are the restrictions on x? Well, x could be 0, right? If x were equal to 0, that would mean that Jill is swimming directly across the river. And so she would be running the full 100 meters. So x can be 0. So I'm going to say x has to be greater than or equal to 0. And then the most that x could be would be 100. Right? And that would be if she swam directly to the finish line and didn't run at all. Right? Because x basically represents the amount, the distance that she's not running. So she wouldn't be running 100 meters in that case if she just swam from the start to the finish line, which that is also a possibility. So looking at the critical value, the negative 21.822 wouldn't work, right? That's not within the domain of our optimization equation. But the positive square root of 10,000 over 21, which is approximately 21.822, that does work. And because our optimization equation is defined on a closed interval, and it is a continuous function. So if you go back up to look, right, there's no domain restrictions between 0 and 100. So t would be continuous between 0 and 100. So that means extreme value theorem applies. And we'll use our endpoints as well as our critical value. And I'm going to use the exact value for the critical value. And this would be a good time to store that critical value on your calculator so that when you're typing into the time equation, you're not having to type in the square root of 10,000 over 21, which I'm sure simplifies, well, yeah, it definitely simplifies a bit. So I'm typing that exact value in. I hit the stow button, right? The button right above the on button. And then alpha, pick a letter. I'm just going to use A and enter to store. Oh, I accidentally typed the wrong value. Store, alpha, A, enter. There we go. Okay, so then I'm going to plug each of these values into our equation for time that's written in terms of x. So this first one would be the square root of if x is equal to 0, so that would just be the square root of 2,500 divided by 2 plus, if I plug in 0 for x, so that would be 100 over 5, which is actually 25 plus 20, or 45 seconds. Okay, and then if I type into my critical value into our time equation, so I've used the letter A for x. That's what I stored it under in my calculator, so I'm going to write in A here just to show that. Divided by 2 plus 100 minus A divided by 5. And it makes it a lot easier than having to type in that exact critical value multiple times, especially in this particular equation where we have a bunch of fractions. Okay, so I get approximately 42.913 seconds, so like approximately 43 seconds. And then plugging 100 in. Well, that would be 100 minus 100, which is 0. So square root, oops, that's not the square root. square root of 100 squared plus 2,500 divided by 2 is approximately 55.902 seconds. So approximately 56 seconds. Okay, so when x is equal to our critical value, that is going to minimize the time. That's our minimum time. Jill's minimum time. And the question is asking toward what point on the opposite side of the river should Jill swim in order to minimize her total time? Well, we can use the approximation of our critical value, so the 21.822 meters, we can use that value to describe the point she's going to swim to. So to summarize, for Jill to minimize her time, she must swim approximately 21.822 meters, so almost 22 meters downstream. So in the picture, that means that x, right, this, get another color, so in green I'm going to highlight it. This distance here is just under 22 meters. So she needs to swim approximately 22 meters downstream in order to minimize her time.